Hi everyone, it's Mr. Baker here with another physics video. Today we're going to be looking at the life cycle of a star. Okay, so today we're going to be looking at the life cycle of a star. The cosmos is within us. We are all made of star stuff. Carl Sagan, an American astronomer, said this. But what did he mean? We'll answer this by the end of the lesson. Hydrogen and helium are the most abundant elements in the universe. But what's an element? An element is a substance whose atoms all have the same number of protons. Another way of saying this is that all of a particular element's atoms have the same atomic number. And what does abundance mean? The abundance of something is just how much of it there is. How are elements made? Well, hydrogen was the first element created after the Big Bang, and we'll look at this in another lesson. All other elements have been made in stars or because of exploding stars, and we'll have a look at that in this lesson. So a star is formed from a nebula, a giant cloud of dust and gas, mostly hydrogen and helium. Gravity acts between the particles in the nebula and pulls them in towards each other. As the cloud collapses, pressure squashes the hydrogen gas so much that fusion occurs. The hot, dense core of the cloud becomes a star. Not all this material ends up as part of the star. The remaining dust can become planets, asteroids or comets, or may remain as dust. A star gives off light because it's so hot. Part of the electromagnetic radiation it emits is the visible spectrum. 99% of a star's radiation is ultraviolet, visible light, or infrared. Main sequence stars, like our Sun, are in the main stage of their life. Stars are fusing elements together. In stars the size of the Sun, hydrogen is fusing into helium. Their size remains constant for millions of years. Fusion inside the star maintains their energy output. The pressure produced by the outward radiation from fusion balances with the gravitational forces pulling inwards. When a star runs out of light elements to fuse, the core gets smaller because of gravity. This increases the core temperature and allows heavier elements to fuse. The star expands, and so the surface area gets larger and cooler. This means the star changes colour and becomes a red giant. Our Sun is in the middle of its lifetime. It is a main sequence star right now, but in about 5 billion years it will die. When fusion slows down due to the lack of elements to fuse, the forces pushing the surface of a star reduces as radiation also stops. Gravity overcomes this outward pressure, and so the star collapses. As it collapses, it heats up and turns yellow, then white, and it becomes a white dwarf. As the white dwarf gets colder, it will turn into a black dwarf, a dead star not radiating energy at all. This process could take millions of years depending on the size of the star. Heavier elements up to iron are produced in the largest stars. When there are no more fusible elements, a large star will collapse very quickly and explode into a supernova. The heat generated by this gives larger elements' nuclei enough kinetic energy to overcome the repulsion between them. They then fuse into all the other heavier elements that we find in the universe. After a supernova, the explosion compresses the core of the star into a neutron star or a black hole depending on the mass. Neutron stars are extremely dense objects made only of neutrons. If a dying star has enough mass, a black hole is produced. They are objects that have such a large gravitational field, not even light or any other form of EM radiation can escape. Stars are born in stellar nebulae. As the gas and dust compresses, protostars are formed. Protostars are like a star fetus. Nuclear fusion hasn't quite started yet. For low-mass stars, after the helium has fused into carbon, the core collapses again. As the core collapses, the outer layers of the star are expelled. A planetary nebula is formed by the outer layers. The core remains as a white dwarf, eventually cools to become a black dwarf. Massive stars will fuse heavier and heavier elements together in an attempt to stay alive and turn into red supergiants. They will then undergo a supernova explosion. If the remnant of the explosion is 1.4 to about 3 times as massive as our Sun, it will become a neutron star. If the core of the massive star has more than about 3 times the mass of our Sun, after the explosion, it will do something quite different. The force of gravity overcomes the nuclear forces which keep protons and neutrons from combining. The core is thus swallowed by its own gravity and becomes a black hole. So that's the end of this one. These are the things you should be able to do. You should be able to identify the sequence of development for a star like the Sun, where we are in the sequence now, and state that changes in fusion change a star's appearance. You should be able to compare the life cycle of small, medium stars and large stars, and you should be able to describe what forces are acting in a main sequence star. You should be able to describe how light elements are formed, and you should be able to describe the features of neutron stars and black holes. You should also be able to explain how heavy elements are formed. So that's the end of this one, and this is what we asked at the beginning. The cosmos is within us. We are all made of star stuff. What was Carl Sagan saying? Well, he was basically summing up the fact that the carbon, nitrogen and oxygen atoms in our body, as well as the atoms of all the other heavy elements, were created in previous generations of stars over 4.5 billion years ago, spread throughout the universe by supernova explosions. Okay, so that's been the life cycle of stars. This has been another physics video. I've been Mr. Baker, and I'll see you next time. Thanks very much.